This is the mission for organized by Spaceships and Logistical Operations. Today we have a presentation of Varsha Shankar. Varsha will be talking about how would be operation of a launch center. Varsha, you are welcome to share your thoughts and to do your presentation. Okay.
Thanks so much, Julio.
So much.
Okay. So I'm going to be talking about the Launch Center today. Let's start out by laying out the agenda. So hello, everyone, and a very good afternoon to all. We'll be covering the role of the Launch Center in the habitat, some technological and design considerations, and we'll then look over a visual concept as well as duties of the crew stationed in the Launch Center. And finally, we will end with learnings that can be borrowed for terrestrial applications. So let's jump right into it. The launch center is the part of the habitat that is responsible for arriving and departing spaceships. These ships could be bringing cargo, equipment, people from cis-Martian space. And for simplicity, I have categorized the launch center's roles into 3 buckets. So let's start with the first. The first is for it to act as a spaceport. The role in this regard is akin to airports on Earth. So ships with cargo and people will arrive and depart from these facilities. Fueling of ships, maintenance of equipment will also be part of the operations. And in a future state, traffic control and scheduling of ships will also be required. Given the dusty Martian atmosphere and fluctuating temperatures, ship will need to be secured on the premises. And the final concern will be building and maintaining the launchpad region. Now, the second category describes logistical operations. Cargo and people will need to be shuttled between the launch center and other facilities within the habitat. And the final category is mining. Our current habitat overview does not have a separate facility for this activity, and it's likely that we won't need one at first since traffic in the launch center will be quite scattered and infrequent. So during the downtime, fuel and water may be generated from Martian regolith, and storing these excavated materials as well as transporting them to other parts of the habitat will be required. We now move on to technological considerations. So beginning with reusable rockets, the kind that SpaceX's Falcon and Starship have made pretty famous by now. These ships will need to bear the repeated onslaught of escaping Earth's gravity, a 6 to 9 month journey to Mars, descent through the Martian atmosphere, and in the worst case, withstand dust storms and temperature fluctuations as well. A viable alternative could be to develop infrastructure that's in waiting in low Mars orbit to handle the last mile journey. Another ongoing area of research is return of samples and materials from Mars to Earth. The image that you see on the right is a conception of what that mission might look like, slated for like 2030 to 2035. It involves a Mars rover packing samples that is picked up from the surface into test tubes, sealed within a titanium container, for protection. An ascent vehicle that would have previously landed on Mars and autonomously deployed relaunch capabilities will launch itself to rendezvous with an Earth orbiter vehicle. And using closed-loop guidance, it would navigate to lock and transfer the container of samples. The orbiter would then release the container within Earth's atmosphere for delivery. The container would need to itself be able to withstand both launch from Mars as well as atmospheric re-entry into Earth. And thinking ahead to fuel systems, solid fuels are single start, but we're super familiar with their usage. Spirit, Opportunity, Curiosity, and most recently Perseverance have all used solid rocket fuel boosters. SpaceX's Raptor and Merlin engines both use a liquid fuel system. One uses methane, another RP1. A hybrid fuel system would use a solid fuel, such as something backspace like SP7, along with a liquid oxidizer. It allows for multiple starts, like a liquid fuel system, but unlike current liquid fuel systems, it has more stable low temperature performance, which would be excellent for temperatures at Mars that range between 20 degrees to like minus 73 degrees on any given day. It's still pretty hard to achieve high levels of thrust in a safe manner and is still under current development. So moving ahead to Launchpad construction, a ship taking off and landing on the Martian surface will generate clouds of dirt and dust, leading to cratering and increased likelihood of instrument damage. Launchpad construction strategies to mitigate damage due to plumes will therefore be important. Two options presented here include a robotically paved and maintained area and an in-flight alumina spray or FAST. Paving the area is an expedient solution, so the paving materials could be made from highly compressed regolith, for example, in situ. In FAST, however, alumina is injected into the exhaust process during landing, so all of that is carried on board the rocket itself. The alumina would then cool on impact with regolith and form a layer much like the paving would to prevent cratering. In terms of fuel generation, Martian regolith could be used as a source of oxygen, hydrogen, and water. And here you see the Racer excavator. It consists of teeth drums on the periphery and hollow drums for storage in the middle. As the teeth drums rotate, the dug-up excavator gets loaded into, the dug-up regolith gets loaded into the storage drums. And the current concept does not currently handle large chunks of ice that are likely to be encountered in regolith, and that will be an ongoing area of research. And large-scale production will require many, many such racers. And to control multiple decentralized robotic systems, you would use the common terminology would be like swarms. So those swarm robotic systems will protect against failure by sheer redundancy. All excavated regolith will need to be then heated to a high temperature to extract water. And following the Sabatier reaction, it can be electrolyzed into hydrogen and oxygen. Hydrogen should be stored in liquid form, such as methane, by combining hydrogen with carbon dioxide, which is plentiful in the Martian atmosphere. In MOXIE, for example, an experiment that is on board Perseverance, we'll be testing out how solid-state electrolysis of carbon dioxide can help produce oxygen. Methane and oxygen will both be stored cryogenically for use within the habitat. So let's move on to some considerations of the design itself of the launch area within the habitat. They've been noted here, and we will discuss each of them in the next few slides. So autonomous function enabled by robots is going to be critical. We are unlikely to have too many humans during the first mission because generating sustenance in terms of food and water is going to be quite hard to begin with, which means swarms of robots will have a distinct advantage, as will any robotic machinery. The swarms in particular will not have single points of failure for the mission. They could be used for things like mining regolith, clearing pathways within caves and lava tubes, and autonomous exploration of the neighboring area. The pictures that you see in the bottom are Off-World's artistic concept of swarm robots on Mars, and on the right you have NASA JPL's lemur climbing robot that we'll look at a little towards the end. Should every facility produce food? Well, it's quite likely, since real estate will be pretty limited within the habitat. And although the habitat will have its own greenhouse, additional food production systems are a good way to ensure redundancy and self-reliance during adverse conditions, such as a dust storm that may have sealed off different facilities from each other. Ships stationed around the habitat should not be left untethered or exposed to the elements. Dust storms and daily temperature variations between 20 degrees to minus 73 degrees can cause quite a bit of damage. What you see here is just a mock-up of what a dome structure might look like that would close and open on its own to keep ships within its premises safe. And finally, since human and cargo movement will be required throughout the habitat, routes that have these structured movements will need to be regularly maintained and kept clear of debris. Again, we foresee having robots having to do most of this work. So let's move on now to what a possible visual concept could look like. An underground habitat is attractive for the benefits it could offer with respect to shelter and safety from radiation, micrometeorites, dust storms, and temperature stability. Talking about the lava tubes in the Tharsis region, now, Mars's gravity is about 38% of that of the Earth's, which allows the lava tubes on Mars to be much, much bigger than those found on Earth. The challenge, of course, is that the exploration of the cave system itself will need to be conducted. And although climbing bots could achieve most of this, eventually we will need to build ramps to ensure human access from the surface. Redirecting sunlight into the cave system itself will also be important. And the presence of sharp, rocky material, or shifting boulders, or even uneven floors could pose quite a big challenge to inflatable habitats that might be housed within the lava tubes themselves. So in the early days, what you see here on the screen is AI Space Factory's multi-layered 3D printed habitat, and it offers an overground habitat solution. Um, on this slide, you see Four Planet Logistics, which has imagined a fully underground facility with astronauts inhabiting lava tubes in inflatable habitats such as the Bigelow. And of course, you see the ramp, which kind of leads from the surface down into the lava tube. And the sources of light or skylights or redirected sunlight from skylight regions. So in this case, I propose a hybrid approach. Overground facilities for launch and storage of excavated and slightly more dangerous materials such as fuel that will intentionally be kept further away from facilities, and an underground region, if found viable, of course, which would include living areas, kitchens, greenhouses, logistics, and water stores within inflatable habitats themselves. When we talk about materials and machinery that might be required to develop the habitat, I've listed a few here as highlights. So 3D printing on Mars. Very likely that we're going to use 3D printing in some shape or form. And ABS pellets are very likely to be a material that we want to work with. ABS, however, is not available in situ on Mars, which means we'll have to carry all of this as cargo from Earth. Basalt is available in situ. However, um, mining basalt itself on Mars is an unsolved problem, as is composite material pellet creation on Mars. But basalt, when extruded and mixed into ABS, would really increase tensile strength and hardness of any printed objects using that composite material. If Martian habitats will be sustained within lava tubes, robotic exploration of these caves will require bots that have the ability to either climb and or to fly. Solar-powered Ingenuity on board Perseverance will be testing out flight on Mars for the first time in human history, while JPL's lemur foot, which is shown in the images on the slide, have been tested out on Earth as a climbing mechanism. A hybrid, which is a combination of what Ingenuity offers right now, that can land and perch on vertical surfaces, would be possible with the merger of both of these concepts. So let's move on to duties and positions that would be required within the launch center. I envision three central positions within the launch center: a launch and logistics manager, person who takes care of arriving and departing vehicle and ensuring that transport and logistics within the environment itself happen seamlessly, a robotic system operator who would ensure smooth operation of any robotic machinery in the premises, and finally a rotating crew member to allow for learning to be distributed and to build redundancy into all human operations within the habitat. Some of the duties, this is a non-exhaustive list, but the highlights will include drills that are run for negative scenarios, monitoring and maintenance of equipment, scheduling, development, and use of communication protocols to ensure smooth transportation of cargo and humans will also be important. Storage and maintenance of robotic machinery from excavation operations, landing pad construction, and exploration will also be required. Sensor health checks, recalibrations of machinery to correct for onboard navigation systems should also be incorporated within system monitoring and health checks. And finally, we come to what learnings we can really borrow for us here on Earth. Reuse, recycle, and adapt solutions to utilize in situ materials, which will avoid excess transportation and minimize emissions. Resources are scarce on Mars, so we're kind of forced to have that kind of behavior on any space habitat. But they're also scarce and limited on Earth, just to a very different degree and different scale. So consuming the least amount of required resources to accomplish the task at hand just makes sense, and it will extend their availability over generations to come. Minimizing the impact of technology on habitat will also prevent their ultimate destruction. Robotic machinery on Earth tends to be scaled depending on the size of the task. Think of the large Earth diggers. Thinking instead about smaller, lighter, and more modular robots that are numerous will change our paradigm on how we use redundancies that are baked into such systems to accomplish simple tasks. I'm talking, of course, about swarm robotics. And finally, use local. And that's all I had for today. Um, these are my references, and thank you so much.